To prove that an infinite-dimensional dynamical system reliably contracts over time, computational dynamicists look for a strict mathematical limit. The standard approach relies on floating-point algorithms to find an eigenvalue strictly less than 1. For a rigorous mathematical proof, however, this method is invalid. Standard processors calculate using rounding. In highly distorting systems, these machine-level truncations generate microscopic false positives, mathematical illusions of contraction that do not actually exist in the equations. Relying on an approximate computational guess falls short of the scientific standard for stability. Verifying these complex operators requires a mathematically exact, machine-checked certificate. The challenge is building a computational engine that guarantees the spectral radius contracts, explicitly isolating and neutralizing machine error along the way. Without a rigorous verification pipeline to trap these floating-point hazards, any computational claim of stability in an infinite system is mathematically thin. A common early step is deploying pure scalar multiplicative Lyapunov functions. Yet across these infinite systems, those functions consistently fail to prove uniform contraction. The underlying reason for this failure is a structural block known as a combinatorial obstruction. This tower represents the 5 mod 6 progression in Collatz accelerated maps, asymptoting to a firm limit line at the integer 2. Because this floor remains locked, no scalar exponent can prove contraction. To bypass this limit, dynamicists adopt a state-dependent finite Markov partition. The computational objective shifts to linear algebra, finding a positive Perron-Frobenius vector where the transition matrix K yields a strict contraction rate. Shifting to a discrete finite grid successfully sidesteps the scalar limit, but it requires a new architectural strategy to account for the residual mass that falls outside the grid boundaries. This creates a core operational tension, mapping an infinite-dimensional system onto a finite computational grid without ignoring the infinite tail of the data. We format the system into an M-matrix block structure, M equals I minus K. The top left blue block isolates explicitly tracked finite states, looping cleanly between known cells. The orange borders form the overflow state, collecting all untracked mass stretching to infinity. Deleting this overflow mass would destroy the mathematical validity of the proof, as it ignores the mass that inevitably returns to the finite system. Instead, the overflow row is programmed to assume the absolute worst-case scenario for any returning mass. We apply standard integral calculus to the infinite tail to calculate the maximum possible mathematical expansion, assigning that upper bound to the overflow state. If this carefully bound system is proven to be a non-singular M-matrix, the spectral radius of our original transition matrix is mathematically certain to remain less than 1. By caging the unknown into a strict, conservative worst-case boundary, this allows us to effectively manage the infinite dynamical tail. Even with a perfectly bound M-matrix, utilizing standard floating-point operations to calculate the inverse remains mathematically invalid. We require a rigorous computational alternative, known as interval arithmetic. Rather than treating a variable as a singular point, interval arithmetic tracks every single value as a strict bracketed range, a minimum and a maximum. By ensuring the true mathematical value is always trapped securely between those upper and lower bounds, we eliminate rounding errors. But direct interval matrix inversion triggers a fatal mechanical flaw. As this interval bracket undergoes a matrix inversion pivot, the numerical boundaries aggressively expand outward cubically, quickly reaching negative and positive infinity. This is the interval dependency problem. Because variables repeat during inversion pivots, the calculations multiply the uncertainty, artificially inflating the intervals with every step. Once the bounds reach infinity, all mathematical precision is lost and the proof fails. In the quest to eradicate computational uncertainty, those strict boundaries compound until they destroy the mathematical model they were meant to protect. To bypass direct interval inversion, we use a specialized architectural mechanism known as the Krawczyk operator. The first step of the Krawczyk method is to isolate the precise numerical midpoints of our inflated interval matrix. We then run those midpoints through a standard, non-rigorous floating-point inverse calculation. We define this newly generated approximate inverse as the matrix R. We isolate the slope matrix by subtracting the product of R and M from the identity matrix. Since R is a highly accurate inverse, R times M perfectly mimics the identity matrix. Subtracting them leaves only microscopic interval ranges. Performing this subtraction neutralizes the macroscopic numerical shift of the entire system. What remains trapped inside the slope matrix is the pure, isolated interval variation, the core distortion of our original map. When we multiply this microscopic slope matrix against a bounding box, it suppresses the interval widths, preventing them from compounding. The Krawczyk operator utilizes a fast floating point guess as a dampening field to trap interval error, achieving strict mathematical rigor. The final hurdle of the verification pipeline is translating this dampened interval data into a rigorous topological proof of invertibility. We secure the dynamical system by applying Banach's fixed-point theorem. The theorem dictates that if an operator maps a defined spatial boundary strictly into its own interior, a unique exact solution must exist within that space. We apply this directly to the Krawczyk operator. Here we establish a tight, semi-transparent 3D bounding box that represents our maximum interval boundaries. As the operator processes this bounding box, the resulting calculated values formulate a denser structure that falls strictly inside the original exterior walls. This strict geometric containment mathematically guarantees that the exact true inverse of our infinite-dimensional matrix lives safely inside the boundaries. By securing this topological enclosure, researchers capture the asymptotic behavior of an infinite, chaotic system within a strictly finite computational cage. The final verification step requires inspecting the strict lower bounds of the resulting interval inverse. If every single lower bound in the matrix remains strictly greater than or equal to 0, the matrix is decisively proven to be a non-singular M-matrix. Achieving this non-negative inverse explicitly proves that our original transfer operator strictly contracts over time. We have bypassed floating point hazards, bound the infinite tail via worst-case overflow, and defeated cubic interval inflation. This specific computational architecture produces a rigorous mathematical certificate of uniform residual contraction.